Today's objective is to solve systems of equations, but instead of graphically, we're now going to use a method called substitution. The basis of this process is to replace a variable with another number or expression so that we're only working in one variable. And once we solve for that one variable, we plug in that value to solve for the other variable. So if you look at this first example here, I've given you the most basic example of substitution you could have. In the top equation, we're given y equals 6, and in the bottom equation, 7x minus y equals 15. If y equals 6, I've already given you one of the solutions. I've told you that in your x comma y ordered pair, the y equals 6. Here, we need to solve for x. And so in this second equation, we're going to replace the y with 6. So the equation becomes 7x minus 6 equals 15. From here, it's a two-step equation. Add 6 to both sides, 7x equals 21. Divide both sides by 7, x equals 3. And we're done. We've gotten the x-coordinate for the ordered pair, and instead of graphing these two lines, we just figured out the point of intersection algebraically. This represents the ordered pair that makes both equations true. We're going to go ahead and keep working with this and look at the second example here. So you should recognize that second equation is the same, but in that first equation, I've now put a variable x. It's going to be no different, it's just that we don't have either variable, so we need to get everything in terms of one variable, solve for it, and then plug back in to get the other. So if you notice here, y equals 2x, I'm still replacing the y with 2x. And so 7x minus 2x equals 15. From here I can combine like terms, 7x minus 2x is 5x, divide both sides by 5, and I get x equals 3. So in my ordered pair, this point of intersection, I have 3 as the x-coordinate, and now we can plug back into the first equation, which is the simpler one, or the second equation, to solve for y. And if we set this up, y equals 2x, y equals 2 times the x-coordinate we just got, which is 3, and so y equals 6. And so I found the ordered pair that's supposed to make both equations true. I know for sure it makes the top equation true. You can do a check using the second equation because we don't know that 3 comma 6 works in that one yet. And so the second equation is 7x minus y equals 15. If I plug in, instead of 7 times x, 7 times 3, and then I subtract the y, which is 6, and see does it equal 15, 21 minus 6 does equal 15, and so I have identified correctly the point of intersection that makes both equations true. Let's go ahead and take a look at a more complicated example yet. So if you scroll down to the third example here, now instead of two numbers multiplied, I have an expression with subtraction, but again, it's going to be no different. I have y equals x minus 2, and so in this second equation, since y is the same thing as x minus 2, I'm going to plug in that whole x minus 2, which means we need parentheses. So 2x plus 2, and then that whole expression, x minus 2, and then equals 4. So the only thing I did is I rewrote the second equation, and instead of y, I plugged in what y equals to based on that first equation. And here it's a good point to stop after doing the substitution, which is what the method is named for. Make sure you have the same variable, and I only have x's here, so I am on the right track. And now it's equation solving from Unit 1. So first I would distribute. Maybe you want to change it to plus a negative 2 to keep track of those negatives. 2x plus negative 4 equals 4. I can combine on the left-hand side. 2x plus 2x is 4x, plus negative 4 equals 4. Add 4 to both sides. 4x equals 8. Dividing both sides by 4, I get x equals 2. And so in my ordered pair, the point of intersection, I get 2. Now I want to back solve or plug in the x to figure out the y. And so y equals x minus 2. Y equals, well, we just got x to be 2. Minus 2 would give us y equals 0. If we wanted to test if that solution is correct, we would go ahead and use the equation we did not use for the back solve, which is the 2x plus 2y equals 4. And so here, instead of 2 times x, I'll have 2 times 2, which is what we got for x, plus 2 times instead of y, we got 0 for y, equals 4 with a question mark because we want to make sure that both sides are equal. 2 times 2 is 4, plus 0 equals 4. Indeed it does, so we did solve this system correctly. Let's try one more. If you take a look at this last example, you'll notice that instead of a y equals, you're given an x equals. And so it's going to be the same thing. If x equals y minus 4, then in this second equation, I'm going to replace the x with y minus 4. They are the same thing. And so my equation becomes negative 4, and then in parentheses, I'm plugging in what the x is equal to from the first equation. And I'd ask you to take a minute right here, make sure that this looks okay. Instead of in that second equation, the x, I've just plugged in the y minus 4. Otherwise, everything else has stayed the same, the negative 4, the y, and the 1. I just replaced the x. And here, too, is a good time to check. I have one variable, so I know I've done my substitution correctly. And now it's equation solving. Distribute, negative 4y, plus 16, negative times a negative is a positive, plus 1y equals 1. Combine like terms, negative 3y plus 16 equals 1. Subtract 16 from both sides, negative 3y equals negative 15. Divide by negative 3 on both sides of your equation, y equals 5. So I have the y coordinate this time, and I need to back solve for the x, which I can use that top equation for pretty conveniently. So here I have x equals y minus 4. I got that the y coordinate is 5. So instead of y, I'm plugging in 5. 5 minus 4 is 1, and so I'm arguing that's the x coordinate. To check, we can use the equation we did not use above, which is negative 4x plus y equals 1. Negative 4 times the x coordinate that we got is 1, plus the y coordinate we got is 5, equals 1. I got negative 4 plus 5 equals 1, and that is a true statement, and so I've gotten the correct solution. Let's go ahead and try one word problem application. Looking at this example here, we have the length of a basketball court is 5 yards more than 3 times the width. The perimeter of the court is 170. Solve for the length and the width. And so what I'd encourage you to do is pull out information that you know. I'm hoping that you recognize perimeter. And for a rectangle, you have 2 lengths and you have 2 widths. And perimeter is the distance around the rectangle. So you can represent this in one of 2 ways. You can represent this as 2 widths plus 2 lengths is equal to the perimeter. Or if you really like to break it down, the perimeter is the width plus the length plus the width plus the length. Or you can add the widths next to each other, the lengths next to each other. You do need to understand that perimeter is adding the sides together. Looking back at the sentence, we were given the perimeter is 170 yards. And so instead of the p in these equations, I can go ahead and substitute the 170 in, and that becomes one of my equations. So maybe for equation 1, I'm going to write 170 equals 2 lengths plus 2 widths. Again, you guys could also write, if you'd prefer, 170 equals length plus width plus length plus width. And so that's one of the equations that we have to work with in this problem. The other equation to solve for the length and the width is going to come from that first sentence. And what I'd recommend is go ahead and replace each variable as you go. And so for the length, right away, I'm going to, instead of length, write L, since I used L to represent the length in that first equation. So the length of the basketball court is, you should recognize, is the key word for equals. And then we have 5 yards more than 3 times the width. And so I'm going to work with that end of the sentence and represent 3 times the width as just 3W. And then to do 5 more than that, I would add 5. And so I'm arguing that the second equation I'm going to use is L equals 3W plus 5. From here, I'm not sure if you recognize, but this is a problem super similar to what you saw in the previous basic examples, where I have this plain variable over here, like the y equals or the x equals, so I'm going to substitute in this expression for the L in the first equation this time, since I want to get the same variables. And so I'm going to rewrite the first equation exactly as is, except I'm going to substitute in the 3W plus 5 for the L. And again, stop right here, make sure this makes sense. We have the 170, the 170, 2, we have the 2W plus 2W at the end. And so the only thing that I changed in this equation is the L, and I made it come to 3W plus 5 since that's what it's equal to. And then from here, it's just like the other problems, it's solving a multi-step equation. Distributing the 2, 170 equals 6W plus 10 plus 2W, combine like terms. We have 170 equals 8W plus 10. Subtract 10 from both sides. You'll get 160 equals 8W. divide by 8 on both sides, and we get the width of the rectangle is 20. I'd ask you to go ahead and write that on one of the spaces. The units in the problem are yards, so be sure to label your answer with the correct units. And then we need to figure out the length. And so if you look at that second equation, or even if you look at that first sentence in the word problem, it says the length is 5 more than 3 times the width. And so I need to use the length equals 3 times the width plus 5 more than that, to figure out the length. So from here, the length equals 3 times, we just got the width to be 20, plus 5, length equals 65 with units, yards. Now checks will be optional, the test will be optional, but a nice way to check this is to see, do 2 widths plus 2 lengths equal 170? We were given the perimeter is 170, and so we want to see, does that equal 2 of the lengths plus 2 of the widths? 2 of the lengths is 130, 2 of the widths is 40, and that does equal 170, so it's solved correctly.